Okay, we had started talking about the emission spectrum in class, but we didn't get very far, so let's start again. Okay, so an emission spectrum, and we're going to do a lab on these. Okay, to get an emission spectrum, you need gas, and usually the gas is in these really delicate glass tubes. Okay, whoops, wow, am I ever an awful drawer? The two ends were supposed to be wider. And then you put them inside on a source that, what's this called? It's not an spectrometer, I think it's called. Yeah, that's what it's called, spectrometer. Okay, so it has a little slot. You plug it into an electrical outlet, and what it does is it runs electric current through the gas, and so it heats the gas to the point of incandescence. Incandescence, to the point where it gives off light. Okay? Okay, and when it gives off light, it glows. We see it, just like the burner on your stove might glow, or the element in your oven would glow whenever it gets hot enough. So we run electrical current through this so that it glows and it gives off light. Okay, now the gas is under low pressure, and it gives off, I should say, radiation. Some of that radiation will be in the visible range, some of it won't. Okay, so heated to the point where it emits radiation. But now what we know is that it's going to emit radiation of only certain wavelengths, certain frequencies, and not others. Okay? The radiation that's in the visible range we will see. The ones that aren't in the visible range we won't be able to see, but like we could hook it up to a computer and they would detect it. But what's actually happening, let's pretend this is hydrogen, okay? So we're going to put a hydrogen tube in here. And we will do hydrogen in the lab. So we all know that hydrogen N equals 1 is negative 13.6 electron volts, and N equals 2 was negative 3.4 electron volts, and N equals 3 was 1.51 electron volts. See, all those questions were worth it. And then 4 is closer, and then 5, etc. Okay? And so when hydrogen gas is just minding its own business, the little hydrogen electron is down here. When we heat hydrogen gas to the point of incandescence, what we're doing is all those hydrogen atoms, the electrons getting excited. And in some of the atoms, it's jumping up to the N equals 2. And in some of them, it's jumping up to the N equals 3 and the N equals 4, etc., etc. Okay, so that's what's happening when we run electrical current through the glass tube to heat it to the point of incandescence. Okay? But these little electrons, when they jump up there, they're all excited when they go up there, but they're kind of like little kids that are going to a friend's house for a sleepover. They're all excited to go, and they're going to sleep over, but then they're there like an hour, and they're like, I want to go home. Well, these little electrons are the same. They jump up, but not very long. They do not last an hour. It's much shorter than that. They're up there, and they're like, I want to go home, so they fall back down. And when they fall back down, they give off that energy that they absorbed. So we're using the electrical current that we're running through them to excite them. But now when they fall back down, they emit that radiation. And if it ends up being in the visible range, we will see it. So if it's in the visible range, the light that it gives off then we can look at through a prism. Okay? So you need to look at that light through a prism, and it will break the light that they give off up into its component colors. We use a thing that's called a spectroscope. Okay, and a spectroscope, it's the ones we have, they're black, they look like this, and they have a prism in here that will then break the light up, and you put your eye down here. Okay, and then you will see the different lines of color. Now, in reality, as these electrons fall down from where they were excited, they'll have different energies, and the different energies, then of course, remember, EP is equal to HF. The different energies will have different frequencies, and those different frequencies will have different wavelengths. And it's the wavelengths then that we see as color, right? Remember, you're solving for a wavelength, and then I say, what color is it? And you look in the chart. Okay, so we can then figure out all the different wavelengths that any given element would have in its spectrum. So we call this a spectrum. Okay, so when you're looking inside the spectroscope, it'll be all dark, but there will be lines of color, right? There might be a purple. I don't know if you can see that that's purple. I don't know if I have a blue here in front of me, but a blue, a red. I'm going to make this black, a blue, and actually there's also a green if we're talking hydrogen, okay, in the visible range. Now in reality there will be a whole bunch of other lines in the ultraviolet range and in the infrared range, but we won't be able to see them, okay? So the lines we're seeing then are from the electrons falling down. And so all those questions that you did to figure out the wavelengths, you could then go and say, okay, which one of these wavelengths would be in the visible range? And you could find them. So hydrogen actually has 4 lines in the visible range: a violet, a blue, a green, and a red. The green is extremely hard to see. Remember, one of Bohr's limitations was that he couldn't explain why some hydrogen lines were bright and some were dim. When we do this lab, you are going to have a really hard time seeing the 4th line, right? It's right there. Can't you see it? Okay. But know that the spectra then, the spectrum is matching the electrons as they drop down. Okay, so going back to this emission spectrum then, emission because it's being given off, what you're going to see is a series of bright lines. So the emission spectrum is often called the bright line spectrum because it's black background with the bright lines of the photons that are being emitted as the electrons fall back down. Okay? No 2 elements have the same emission spectrum. So an emission spectrum is like our fingerprints, okay? No 2 people have the same fingerprints. No 2 elements have the same emission spectrum. We can actually identify an element by its emission spectrum, right? So people who study these, if they would take one look at this, say, oh, that's hydrogen. The other day I told you that sodium had 2 yellow lines really, really, really close together. It's really easy to distinguish. Neon has a whole truckload of red lines. Like there's an amazing number of red lines and orange lines in neon. There's no purple at all. There's a couple of blue down here and a couple of yellow. So neon's really easy to recognize. And that's for those of us who don't work with them all the time. So you can imagine that people are working with these, they'd be able to identify an element just by looking at it, okay? So no 2 elements have the same set of wavelengths, so because they don't have the same energy levels, so then therefore they don't have the same emission spectrum, and so they can be identified by the bright lines that they give off, okay? The bright lines then are the photons that are being emitted, and then the dark spots in between are the ones that can't be emitted because they don't match the levels. Okay, this is the visible spectrum. It would have lines in the ultraviolet, in the infrared, in the X-rays, etc. We just can't detect them. So that's the emission spectrum. Okay, gas heated to the point of incandescence and then looked at through a prism so that it will be broken up into its lines. The light that it glows and then the light that it gives off is broken down by our prism so that we can see a series of lines called the emission spectrum or the bright line spectrum. And it's like the fingerprints for the element. Okay, we are now going to do the second type of emission spectrum, and it's called the absorption spectrum.